Hi, everyone. Thank you for coming to this session. In preparing for this, I realized that 3 hours is a lot, and there is so much to say about inference in Kubernetes. But I myself have been working on LLMD for a while now, so I kind of know, and Kubernetes generally speaking, so I kind of know what problems it solved. But I realized that there is so much context that has to be explained before we can get to actually explain what LLMD is. And whether you have never done inference on Kubernetes before, or you have done it, there will be something in this session that will be useful for you, hopefully. So we're going to start with some very basics, explain what is inference in general for Gen AI. Then we're going to go to explain what AI on Kubernetes is and how does running large language models look like. Then, very important, explaining the Gateway API and Inference Extension of the Gateway API. And then we get to the LLMD project itself. And once we are done there, we're just going to all realize that we spent a lot of time talking about network traffic for large language models. But running large language models in production goes beyond just network traffic. And that's the last section, beyond routing. Before I get started, by show of hands, on a scale of 1 to 5, 1 being I have never touched Kubernetes before, 5 being I am the most expert in this room, how many of you have run LLMs on Kubernetes before? Let's say at a 5 level. OK, at a 1 person. At a 4 level? At a 3 level? At a 1 level? All right, most of you. OK, cool. All right. How many of you have never worked with Kubernetes before? Raise your hand. All right, so most of you have. Cool. All right, cool. So let's get started. There is one of the people who is actually working on LLMD is a principal engineer at Google. His name is Clayton Coleman. And he did his talk last year called LLMs is the New Web Applications. And his talk was arguing that running large language models is the new version of running microservices. And that running large language models fundamentally utilizes the same primitives, the same principles, the same exact auto-scaling, monitoring, observability, all of that stuff that we have been doing for web applications and that Kubernetes have been designed to solve. But there is a little asterisk at the end of that statement. And that asterisk is what we're going to be talking about today. We're going to be talking specifically about how large language models are very, very different than web applications. From all measures, sizes of the application, traffic pattern, memory management, resource management, CPU management, device management, and all of that stuff. So I think you have seen probably a version of this slide before. But essentially, Gen AI is evolving very quickly. And the same way those like large language models that most big cloud providers, including OpenAI, including Google, Azure, AWS, are providing, there is also a growth in the open models themselves. So those are the either open source or open weights. But these are models that you would run yourself for many, many reasons, right? And what is interesting is that they're even growing in terms of the complexity of what they can do. 3 years ago, when ChatGPT came out, it was basically generating text, mostly, right? Now we have models that can think. We have models that can generate audio, video, images. We have models that can process very, very large text and summarize it with 128 or 256,000 context window. And I'm going to talk about what context window is in a bit. And at the same way or the same time that there is interest for hosted large language models, there is also a lot of interest for running your own large language models for many reasons. Before I move on, I want to spend a little bit of time explaining some concepts. These are words that you're going to hear over and over during this session. And I think it's important that we kind of all have more or less the same understanding of what they mean. LLM, I think by now everybody knows what an LLM is, right? If you don't know what an LLM is, where have you been under the last 3 years? Inference. So sometimes you would hear the word inference and serving kind of used interchangeably, but they are actually fundamentally very, very different. It's true that we talk about inference in the context of serving, but inference is a very, very specific term. And I'm not pretending to be an expert on this. I'm not an expert in machine learning models. My background is in infrastructure and running large-scale applications. But inference, loosely explained, is what happens when the model sees new data for the first time. So you train a model, or you fine-tune a model, and then you run it, and then you give it a prompt. You give it a text as an input. The text generated as a result, that's called inference. And inference is the internal working of the model itself, how the model gets from input prompt to generate an output, right? So inference is architecture dependent. What we're going to be talking today is basically about the TensorFlow architecture, or the Tensor architecture, which is the main one that most large language models use. But if you're wondering, I can take you probably down the memory line 6 months ago when DeepSeek came out. There was a lot of claims about how DeepSeek was trained with only like $5 million or whatever, and how it's like one of the most optimized large language models, et cetera, et cetera. The reason why the team that actually released DeepSeek managed to make it super efficient is because they rewrote the inference layer. They completely re-architected how the model gets to generate tokens as an output, right? Serving is essentially the act of running the model in production. So you have a large language model, which is a file or a set of files. It is not a binary. You cannot double-click it to run it. You need to execute it somehow. So serving is taking the model and then putting it inside a serving engine. The kind of loosely way I define it, and I know that if you're a machine learning model expert, you're probably not going to like this explanation, but the way I loosely explain it is think of serving as what are web servers for web applications. If you have a web application, which is JavaScript, HTML, CSS, you cannot just run it. You need to run it inside something that will like translate requests coming from you as a user to the web server returning a result, right? And so that's a web server, right? That's your Nginx, your HA proxy, your WebSphere, if you're old like me. And in the context of large language models, a serving engine acts more or less the same way. It gives you a standard API, so you can talk to the large language model, and then it has the capability to talk to the model using whatever the model understands. And so with this explanation in mind, serving engines are model specific. If you are going to run a model on top of a serving engine, you have to go to the details, the technical details of that particular serving engine to know if it's compatible with that particular model you're trying to run. There is a reason, for example, why Ollama, when it was released, they have a page that lists all the models they support. They don't support all the models that exist in the market. They only support some of them. And when a new model comes out, it has to be adapted, and Ollama has to either change their serving engine to be able to run that particular model. Accelerators, I think everybody knows what they are, but if you don't know, they're basically the very specific chips that can be used to do matrix calculation. They're usually GPUs. That's like the one that everybody knows. But there is also a type of accelerator called TPUs, tensor processing units. Those are Google-specific chips, custom chips that are designed to run to run models that have been developed using the TensorFlow library. Quantization. Quantization is a value that you input to the model to change its precision. If a model runs at full quantization, it means that it will be the more precise, but its memory footprint would be the highest. So it's a value that you can tweak to be able to change the memory footprint of a specific model. But by tweaking the quantization value, you're also tweaking the precision of that particular model. Weights, these are the numerical values that define the strengths between neurons. I'm not going to go too much into details. I'm going to explain the last two things. Context window. Context window is very important to know if you're running large language models in production, because the memory footprint of the model and a bunch of what I'm going to be talking about later will depend on the context window. Basically, context window at a very high level is how many tokens the model can ingest in one go, right? Most open models have something like 128,000 context token as a context window. If you go to the cloud-hosted models, something like Gemini or OpenAI, they have 1 million to 1 million context window. Why this is important? Because large language models are basically stateless. If you're talking to a large language model, you ask it question number 1, and then you send the next question. If the question number 2 is related to question number 1, you can take an example. Let's say you write the first prompt, what is the capital of Belgium? It will reply to you, Brussels. But if the next prompt is, how many people live in that city? We as humans would know that we are talking about the context, which is Brussels, right? So if I would ask you this question as a follow-up, you would answer to me X number of people. But if you do this in a model across 2 different chat sessions, chat session number 1, you ask the question, how many people live in Brussels? What's the capital of Belgium? And then you go to chat number 2 and ask how many people live in that city, the model wouldn't understand because it doesn't have the context. So to make models useful, what you have to do is each time there is a new prompt, you have to send back the previous prompts and the previous questions. So as you can imagine, if you have a very long chat session, that context window gets bigger and bigger and bigger and bigger each time, right? So this is something to keep in mind, very important. And then the last but not least is multimodality. Multimodality basically just means that the model understands beyond text. If a model is multimodal, it basically means it understands text, audio, video, pictures, both as an input or as an output, or both, right? So there is a white paper that was released by Google a while ago. And this white paper explains actually the 2 phases of generative AI inference. And these 2 phases are the prefill phase and the decode phase. Most large language models that are based on the tensor architecture implement these 2 phases processing. So the prefill phase, which is compute bound, takes the user input, turn it into tokens. So that's the prefill phase. And we call it prefill because most large language models that run on top of GPU will cache that input. They will write the input into a part of the memory of the GPU that acts as a cache layer. We typically refer to that as KV caching, key value caching. The second phase is the decode phase, and that's essentially generating the actual tokens. That particular phase is memory bound, right? So typically, the prefill phase is done in one large pass. So you take a prompt, you tokenize it in one go, you store it in the memory. In the decode phase, you might do multiple passes over the next token, because basically generating the next token is a statistical computation problem. What is the likeliness of this word being the next in the sentence? And each time you generate next token, the model reread the entire phrase, so it knows more or less what the next token is, right? So in both cases, most models, when they run on GPUs, they will actually cache both. They will cache the results of the prefill phase, and they will cache the results of the decode phase, right? And the reason models do that is to optimize computation. Because if the next question is a follow-up over the previous question, then there is no need to do a prefill. The model will just, or normally not the model, the serving engine, will just read the first prompt, figure out the prompt already exists in the cache, it's not going to run the prefill, and just jump directly into running decode, right? Keep these 2 things in mind. We're going to get back to them in a moment, but keep these 2 things in mind. Next is talking about batching. So most language models process prompts in batches. There are roughly 2 big strategies for batching, which is either static batching. Essentially, you take a bunch of prompts as an input, you put them in a batch, you don't process them, you just wait, and when the batch fills up, you process them in one go. The second phase, or the second strategy, is continuous batching. All large language models or all server engines do this. And most of them, specifically the one we're going to be talking about the most today, called VLLM, has actually a flag for you to change the batch size. If you set the batch size to 1, it will be static batching. So it will fill up the batch, process it, and then fill up the next one, process it, etc. If you set up to a different value, it does continuous batching. Static batching is pretty good for very large prompts. It's designed specifically to optimize for throughput. And that's good if you are doing, for example, processing a book. So you take a book as an input and you want to summarize it as an output. So you do a static batch, you wait for all the tokens to show up, and then you process it. But it's not optimized for latency, because with static batching, you're going to wait for the batch to fill up, so you're not going to start processing until the batch fills up. So latency will be quite slow. Quite high, sorry. Continuous batching will continuously fill up the batch and process it at the same time. And then as more tokens are coming or more prompts are coming, it will just append them to the existing batch and then process it at the same time. So one of them is optimized for throughput. The other one is optimized for latency. Which one do you use? Depend on your use case, depend on the large language model you're running, and depends on the serving engine. To give you very good concrete examples of which one is useful where, static batching would be useful for something like code assistant. Because what you want is you want the entire code base to be batched so you can do one pass and then generate a result. In this particular case, you probably don't care too much about latency because the user, the developer, can wait a few seconds before the token starts being generated. Continuous batching would be useful for a chatbot because chatbots will have hundreds or thousands of users talking to them at the same time. So you want to continuously add prompts from users to the batch and process them at the same time. And you want to optimize for latency, not for throughput. Make sense? Cool. And so I'm going to talk about this very quickly. The two biggest benchmarks that you could run to see which kind of parameters of the LLM you want to tweak are, for latency, are things like the time to the first token. So that's a very good metric to tell you how fast is your model in generating tokens. The normalized token per output token, so how much time it takes to generate one output token, and the number of tokens per second, obviously. For throughput, request per second, output token per second, input token per second, and tokens per second. So these are kind of roughly the metrics you would track to kind of know if you want to optimize for throughput or if you want to optimize for latency. I talked quickly about VLM. VLM is not the only large language model serving engine that exists on the market. There is a bunch of them. There is actually one missing from here. There is Hugging Face, has a serving engine called TGI, Text Generation Interface. NVIDIA has a serving engine called NIM. NIM is very, very specific because what NIM does, or what NVIDIA does, is that they actually take NIM and they package it with a bunch of open models. So NIM is, you cannot just run any model with NIM. When you download a NIM microservice, as they call them, or a NIM container, it's actually containers, so it's designed to run Kubernetes. When you download a NIM container, it's essentially the NIM serving engine packaged with a specific model, with a specific version of specific model. And so you can't just take NIM and put a model on top of it. NVIDIA has to supply you with those particular models. And NIM is, I believe, is paid. You can use it for free up to a certain extent, but it's paid. There is Ray, or Ray Serve, to be very specific. So Ray is an open source framework written in Python. It's designed to do end-to-end machine learning lifecycle, everything from training to reinforcement learning, fine-tuning, blah, blah, blah. But it has a component called Ray Serve. And Ray Serve uses VLLM under the hood. So it's just an abstraction layer on top of VLLM. And then there is JStream, there is Olama, and there is another one that NVIDIA has, I forgot its name. There is also Triton from NVIDIA, and there is another one that they just, Dynamo, I just remember now. It's called Dynamo. So these are just some of the most common ones. LLMD itself is optimized to run VLLM, and we're going to look at that later. So hopefully this kind of level sets a bit the understanding of what large language model inference is. I'm going to jump into doing inference on Kubernetes, and we're going to see a bit of a demo in a second. And then from there, we'll be able to hopefully get into the networking part for the gateway API, and then what does LLMD does. So running AI on Kubernetes. Why would you want to do that? Right? Very good question. Well, multiple reasons. Either regulations. You are part of a regulated industry. You cannot use cloud-hosted models. Privacy is another one. You just don't trust the cloud. You want to run things on your own servers. Latency is another one. You want the model to be as close to the application as possible. Cost would be another one. Most cloud-hosted large language models, they charge you per token. If you want to optimize for the cost, or if you are in a situation where you can't be running in a pricing model that depends on how much tokens the model generates, because you're afraid that your developers will go overboard and generate tons and thousands of tokens and end up costing a lot of money. You want to control costs, so you can just buy hardware, buy servers, and then do the inference yourself in your own data center. Special use cases. maybe that cloud-hosted model is not good for the use case you want. You need to fine-tune the model to your specific data set, or you need to run the model on the edge. One particular use case I have seen in the past is running models on top of oil rigs in the middle of the shore, middle of the sea in Norway. So the oil rig is a platform running on top of the sea, and on top of it there is like a bunch of machinery and a bunch of servers. And one particular use case that I've seen before was analyzing CCTV camera feed and triggering things like alerts, like somebody is about to trip over and fall in the sea or something like that. So you want that to be very, very latency. This is a very latency sensitive use case. You want the model to run as close to that camera feed as possible. Or all of these above reasons, or any of them, right? So running LLMs then, in this case, you basically have three options. You can either do it the fully automated way, which is what you see on your left side. So that's essentially you use a fully managed platform like Vertex AI on Google, Bedrock on AWS, or Azure AI. So that's essentially, give me a model, I give you an API endpoint. I don't want to understand how this thing works. I don't care, right? You can do the right side, which is running on your own virtual machines or bare metal servers, right? Or you can do something in the middle, which is Kubernetes. That's kind of like the middle of both, I would say. By the way, I know that this is going to be recorded, but it's fine. Vertex AI uses Kubernetes under the hood. You don't see it. If you're running on Google Cloud and you're running on Vertex AI, it is just GKE under the hood. So why Kubernetes for open models? Well, multiple reasons, flexibility being one of them. Kubernetes is pretty flexible. It runs containers. As long as your application is packaged as a container, or your large language model is packaged as a container, Kubernetes will run it. Portability is another one. Being able to port your container or LLM from one platform to another. Again, because it just runs containers, so it should be possible to just move it from one place to another. There is a little bit of a caveat. I should have added an asterisk to that portable sentence there. I'm going to talk about it at the end, but there is a little bit of a caveat about or around portability in Kubernetes. I'm going to talk about it. Performance will be one of them. Kubernetes did have a lot of improvements over the last couple of years that actually makes AI models like first-class citizens. So it's not only focused on running stateless web applications or stateful databases, it's also optimizing or being optimized by adding new functionalities for running AI models. One of the most recent ones is an API they added to Kubernetes called DRA, Dynamic Resource Allocation. I'm going to talk about it in a bit. And then efficiency. Kubernetes gives you so much metrics about resource utilization, about scheduling, about latency, that you can actually use those as a way to optimize how your deployment works. So let me show you, starting with very simple example. So I have a cluster here, which I can show you here. This, of course, is running on top of GKE, and it is a pretty basic cluster. What I wanted to show you is my node configuration. I have like 3 node pools. This node pool here doesn't have any accelerators, and I have 2 here. One of them has L4. Both of them has L4 GPUs. This one has 1 L4 GPU per node, and this one has 2 L4 GPUs per node. And the reason I'm showing you this is because I'm going to show you an example where we run a large language model that only runs on top of a single GPU, but that's not the only deployment model you're going to have on Kubernetes. There are cases where you do multi-GPU deployments, which is the model runs on top of a node with multiple GPUs, and the model itself is split across multiple GPUs. And there is a third use case, which is running across multi-host, multi-GPUs. So the model runs on top of multiple hosts just because the model is so big, it cannot fit on a single GPU. You need more of them, and then you run into a situation where you have a physical limitation of how many actually physical GPUs you can have a single server, so you need to split across multiple hosts. And so this is my YAML file. For those of you who don't like YAML, I'm sorry, but I am a huge YAML fan. I am as a self-proclaimed YAML engineer. So it looks like a single deployment, a simple deployment. I have a bunch of labels here. Let's get to the interesting thing. I'm running VLLM OpenAI. So you might be confused. What does VLLM OpenAI means? So OpenAI came up actually with a standard API spec called the OpenAI API spec. It's a very hard to pronounce. The OpenAI API spec is a standard spec that most cloud providers have adopted now. Actually, today, even if you're running on top of Gemini on Google Cloud, you can enable the OpenAI interface for Gemini. So if your application is written such a way that it calls a model through the OpenAPI spec, you can migrate it between models easily. And so this is a VLLM container image, which was packaged with the OpenAI API interface. So this is where we start getting into the interesting stuff. So I want to run it with 2 CPUs, 10 gigabytes of memory, 10 gigabytes of storage, and 1 GPU. So requesting or telling Kubernetes to give you resources, accelerators, is as easy as putting it in the request. There is another thing that you need to do, which is you need to also select something like a node selector. A node selector basically will map this pod or this particular deployment to a node that has this particular label, right? So it will look across all the nodes. It will look at the node that has the label and will go, OK, schedule this pod on this particular node. And then I have also added this. This is just a Google-specific thing, which is installing the latest GPU drivers. To run models on top of GPUs, you need the drivers. This is automatically triggers the installation of those drivers for me. And then I have a bunch of other things, but this is the interesting part. I have the VLLM itself, starting VLLM in Python. I tell it which model I want to run. I tell it how many GPUs are on this particular node that I'm running on. I give it a host and a port to listen to. So it will be listening on all the ports, all the hosts on port 8000. I've already deployed this. Hopefully it's running. No, it's going to be running inside demo 1 namespace. And if I do this and do a -o wide, for those of you who doesn't know, -o wide will tell me which node the pod is running on. This particular node here, if I get nodes, this L4 pool, which is this particular one, this is one of the nodes that has a single GPU. So using a combination of the node selector and the requests that says 1 GPU, make sure that the pod is scheduled on the right node. So one thing I didn't show you, which I'm going to show you now in my deployments, is I also have a secret here. And this secret is a token to access Hugging Face. So this particular mode of deployment deploys VLLM with a vanilla model and then gives VLLM access to Hugging Face so it can download the weights for that particular model. So the VLLM container engine I'm running doesn't have the model inside. It will spin up, and it will download the model from Hugging Face, download all the weights, and then run the model for me. This is like the bare-bone way you would deploy basically anything, but specifically large language models on Kubernetes. So my model is already running. Sorry. Here we go. And I can query it. How do I query it? I need a little port forward because my model is not on the internet. And then I can just do a quick curl command here. I'm going to explain to you what this curl command does. I'm just going to take it with the GQ, open a new tab, and just run my query. So I'm running it on localhost 8000 because of the port forward, /v1/chat/completion. This is the standard API endpoint of OpenAI, right? And then I'm executing a post request, telling it which model, and then sending a prompt. My prompt is wrapped into a messages array, which inside I have a role and the content. Most large language model supports something called system prompts. And system prompts are essentially the prompts that you as a developer will send to the model to tell the model how to behave. In order to mimic that in the OpenAPI spec, they have this structure here, which is a set of messages, and then it's an array, and then in each message there is a JSON payload, and there is a role that can be either user or system, and then the content. Why this is an array? Well, this is basically in order for you as a developer to build that multi-turn chat, that context window, you would just append new messages to this existing array. So you will have a payload with an array, and then each time the user sends a new message, you will just append a JSON payload that looks like this and send this back to the model. Notice a few things. I'm going to talk about it later. I have to pass a model ID as part of my payload. And this is the OpenAI spec. The OpenAI spec has this particular requirement, which is you have to tell it which model ID you're talking to. If my model ID that I'm passing here doesn't match the model ID in my deployment, VLLM will just tell me, I don't know what you're talking about, right? And then I get my outputs. I have my content, so I asked it why the sky is blue, and then now it's explained to me why the sky is blue, right? Very nice. Now, let's do something a little bit more interesting. I want to time this request. I want to see how much it takes for this request to actually run. Keep in mind, this is a very, very small model. It's 1 billion parameter, so it should be relatively fast. It's going to take a little bit of time. And when it runs, it takes about 10 seconds to run, right? So as you can imagine, if I have multiple prompts, if I put this in a loop of 10, it's just going to take even more and more time. So my latency will be very high on the last messages, just because there is batching in place. There is the model itself is not very capable. It's not very big. There is the memory. There is a lot of things. So let me do something. I'm going to try to fix this by doing the thing that most of us will think, which is let's just scale the deployments, right? What's the worst that can happen? Let's just run 2 models instead of 1. And let's see what happens. And I want to use also this as an opportunity to show you the logs. I'm going to run the kubectl logs command to see. Oh, this is going to not run, I think, because I need to kill something else. Yes. Do I need to kill this, or do I need to... Hold on. Let's see why it's not running. I think it's not running because it doesn't have, there is not enough nodes to run the model. All right, so how can we solve this? Do we have something else running there that I can delete? Or is this going to trigger a scale up in my cluster? Because I only have 2 nodes here, but I also have this one. It should run on this one. No. All right, I'm gonna leave it and come back to it in a second. Hopefully, my cluster will scale up and it will run. But I can actually look at the logs of the existing one if you want. Yeah. I think I'm not gonna be able to see the latest logs because it's not gonna. No, I have them. All right, cool. So you see here. This is the beginning of the logs. The beginning, it's basically VLLM will detect that it's running on top of a GPU with CUDA, so it runs that there is like a GPU driver, blah, blah, blah. But the part that is interesting that I want to get to is this part here. Because I am setting VLLM to download the model from Hugging Face, this is the logs that tells me that it took basically 18 seconds to download the model itself. And then it took roughly about half a second to load the weights. This is the logs of downloading the weights themselves. So this is downloading the weights from Hugging Face. And then the model is loaded into 1 GB. It took like 19 seconds. And blah, blah, blah. There is 17 GB of available GPU memory for caching. This is the KV caching I talked about. And then this is more or less where VLLM itself started serving. So you can see that between starting the pod here, let's say this was yesterday, 5:18, and being ready to serve, it took roughly about 2 minutes, right? So it took 2 minutes to download a 1B model and set it up such a way that it's ready to serve. So you can imagine for a much larger model, this is going to take even longer, right? If there is more weights, it's going to take longer. I could influence the time it will take for the model to start by changing the quantization. So if I set the quantization to a lower level, there will be less weights downloaded, and then the model will take less time. But just to give you an idea, 2 minutes for a 1B model. Not too bad. I'm going to do one more thing real quick. I talked earlier about the fact that one of the reasons why you want to run your model locally is the fact that you want it to be as close to an application as possible. So I'm going to show you this as a demo. I'm going to run Gradio, which is an open source chat interface, on the same cluster in the same namespace. And then I'm going to do a quick port forward. And then hopefully this will just work. Yeah, it's working. Hi. Why is the sky blue? And this is just an example of the model itself and the application that talks to the model are just running on top of the same exact cluster, close to each other, right? So well, that goes my answer. That's fine. But that's just to illustrate the example of running local models locally. If Gradio was configured to talk to a model running in the cloud, this will take even longer to get the prompt back. Anyway, back to the slides. So that's like a very basic demo of running models on cloud. On Kubernetes. So I started this by saying this statement, which is LLMs are the new web applications. Now, let's go into the details of why LLMs are actually not your typical web applications. There are multiple reasons, and one of them is running a large language model is only one piece of a very big puzzle. And the bigger puzzle is that you have the large language model itself, which runs on top of a serving engine, which runs on top of accelerators. So you have multiple layers that needs to be optimized. The example in the logs I showed earlier, which is it takes about 2 minutes, more or less, from VLLM starting to downloading the model to loading it into the GPU memory to actually starting the serving part. This is the reason. The reason is because there's multiple layers of how large language models themselves run. And each of these layers can be potentially optimized. Your typical scaling strategies for typical workloads doesn't work for large language models. You can't just make a model faster by just giving it more capable GPUs. Actually, arguably, if you give the model a GPU, which is oversized for what the model needs, you're just going to be wasting GPU cycles, right? There is a way for you to do something called GPU sharing, where you can run on top of the same GPU and then share it across multiple large language models, but that's not supported by all models, and it's only supported in very limited set of NVIDIA GPUs. There is then your vertical optimization strategies, which is just, so that's, what I just explained would be the example of a vertical optimization strategy. Give the model more resources, more memory, more CPU, more GPU. Your horizontal optimization or horizontal scaling strategies also wouldn't work. Just running multiple models, multiple instances or replicas of the same model, because I just have a lot of requests I want to process, wouldn't work. Why is that? Well, so we talked about the model size or the inference image size. So these are just a benchmark of some of the popular open, serving engines with their image sizes. You see here the one I was using earlier, the VLLM OpenAI, is roughly about 5 gigabytes. That's just like the vanilla image. It doesn't have the model inside. This is just some test I was running where I just roughly timed how much it takes for the image to be downloaded. So 1 minute, 55 seconds, roughly 2 minutes. So this is just the time it needs for this particular model, container, which is just the serving engine, to be downloaded. So if we go back to the example I showed earlier, which is Gemma 1B running on top of Kubernetes, it takes roughly 2 minutes-ish between VLLM starting and the model being ready to serve. And then you add another 2 minutes for downloading the container image of the serving engine. That's roughly 4 minutes, right? So as you can imagine, in a scale-out scenario, let's say, for example, you have configured the horizontal pod autoscaler. If you don't know what's a horizontal pod autoscaler, it's just a component in Kubernetes that you can configure it and you can tell it, this is my pod. If the pod resource utilization goes beyond a certain threshold, autoscale. Autoscale means add another replica, right? That wouldn't work because if I am running a single instance and my horizontal pod autoscaler autoscales to the next instance because I suddenly have a lot of traffic coming in, then the next instance will take roughly 4 or 5 minutes to start. That's 5 minutes where I cannot serve traffic, right? So your typical horizontal autoscaling that you can do with web applications doesn't work for large language models, simply because the image sizes are too big, the models themselves are too big. So some of you, or one of you might come and say, okay, well, to solve this problem, let's just optimize on that last 2 minutes it takes to download the model by baking the model inside the container image, right? So we take the VLLM OpenAI container image, and then we pre-bake, we add the model inside. Well, that will just make the container image even larger. And that pool time will be even bigger, right? The pool time if you are confused what pool time means, the pool time essentially is the time it takes the node in Kubernetes to download the container image, right? So the container image is in a container registry somewhere. I do my deployment, kubectl apply my deployment. The Kubernetes schedules the pod, put it on a node. The node has to download the model. That's what you're seeing in the column that says average image pool time, right? So horizontally autoscaling doesn't work. Then I talked about the model sizes. Again, these are some basically how big the images are based on the quantization, and specifically how much GPU or TPU memory needed in gigabytes based on the quantization of the model. You see my Gemma 2 with Gemma 1B here on a full precision needs like 2 gigabytes, and at a smaller quantization needs 0.5 gigabytes of GPU memory, right? So arguably, actually, what the example I was showing is a little bit wasteful because I'm using an L4, NVIDIA L4, which has 24 gigabytes of memory to run Gemma 1B, which needs 2 gigabytes of memory at full precision. What I would have done better is layering a Llama 3, because Llama 3 at full precision needs 22 gigabytes, and that's roughly more or less what an L4 is, or how much memory an L4 has. Now, you see on this table here on the right side, this is something that is done automatically by the serving engine that you're using. You can tweak it. Essentially, your server engine, VLLM in this particular case, because it supports KV caching, it will set a percentage of the memory to that particular thing. So during the prefill phase, I talked about it earlier, it will use this KV caching zone to cache the input tokens and output tokens. By default, VLLM sets about 30% of the memory available in the GPU for KV caching, but you can tweak that, right? So the more KV caching part of the memory you set, the more you're going to optimize for throughput, but you're going to not optimize it for latency, right? So your throughput will be better, your latency will be worse. The more you go toward smaller KV caching, your latency might be higher, but your throughput might be lower. There is a formula if you want to calculate. I'm not going to go into details, but there is a formula if you want to calculate how much memory, GPU memory you need, depending on which model you're trying to run. I'm going to take your attention to the last line, which is DeepSeek. So DeepSeek, the highest variant is the 685B model. And at full precision, it requires 1,370 gigabytes. That's 1.37 terabytes, right? I will probably dare you to show me a GPU today on the market that has that much memory. It doesn't exist. I think the biggest GPU in terms of memory you can find on the market today is an NVIDIA B200, and it has something like 80 gigabytes of memory, right? So let's take the example of the NVIDIA A100 40 gigabytes there that we have on the right side. So roughly out of my 40 gigabytes, I have 26 gigabytes set to run the model itself. 30% is used for KV caching, so that's not going to be useful. So to run this particular model, I need to divide 1,370 by 26. I am lazy, I don't want to do math, so I'm just going to do it in the browser. So 1,370 divided by 26 is going to give me 52 GPUs. So in order to run DeepSeek 685B at the highest precision, I would need roughly 52 A100 GPUs, right? Now, I don't know how much hardware you have done in the past, but you know that there's actually a physical limitation to how many GPUs you can put on a single server. And that limitation is typically how many PCI Express ports are available on that particular server. Normally, your off-the-shelf server will have something like 8 PCI Express ports, which means you can't just take a single server and cram 52 GPUs inside. It's not going to work, right? So in order to run DeepSeek 685, I will have to run on top of 52 GPUs split across multiple physical servers, all of them being fully loaded with GPUs. Make sense? And we're going to talk about this in a bit, or later. It's called multi-host inference. Then the last thing that also to keep in mind, or like one of the things to also keep in mind, is that the way LLMs are very different than your typical web applications is the traffic patterns. A typical web application will have uniform, fast requests. Your REST requests are more or less uniform in size and very fast. So the standard typical load balancing way that, like round robin, let's say just an example, works for web applications because all the requests look the same. They all take more or less the same time to execute. And if for some reason you have a workload that has long sticky sessions or something like a webhook or a sticky session, like a session that stays active for a very long time, well, you can actually easily split them away to a dedicated set of nodes and then run a dedicated load balancer that knows how to handle the traffic. The problem with large language models is that the requests don't look the same. What you see in blue is basically the size of the request. Sometimes the request is very small because the question is, hi, how are you? Sometimes it's very big because it's a book that you're trying to summarize, right? Sometimes they are text. Sometimes they are pictures. Sometimes they are videos, right? So as you can imagine, the typical load balancing that we do for web applications wouldn't work for large language models. If you take a round robin HTTP load balancer, put it in front of a bunch of Gemma 1B models running on top of multiple nodes, it will just end up creating unbalanced load. It will try to load balance in a round robin fashion, which is send one request to each pod, and then by the time it finishes all the list of the pod in the first pass, goes back to the first one, maybe the model is not even done processing the request, and then your request will be just queued by the model, right? So how do we solve this particular problem? So we talked about this. Regular load balancing doesn't work. Load balancing for LLMs needs, if you want to create like an LLM-aware load balancer, you need the load balancer to be able to look beyond CPU and memory. Because your CPU and memory for a large language model might actually not even look like something. Like it might just consume a little bit of CPU, a little bit of memory, because most of the work is done in the GPU itself, right? So you need the load balancer to be able to look at the GPU memory utilization, the KV cache stats, and one extra metric that is very important is the queue size. Essentially, how many prompts are being queued by the model to be processed. If your large language model does media generation, then your load balancer needs to be able to handle long connections to upload media. Imagine you're uploading a 2-hour video. That's going to take a very long time, right? Some of the large language models does also support token streaming. So that essentially means that as the model is generating the tokens, it's sending them back to you, which means also the connection between the client and the server will be sticky and very long, right? So you can receive those tokens. And there is actually, today, I think there is already a couple of models, open models, that support live multimodality. So live multimodality basically means you can talk to the model real time, bidirectionally, in both text, audio, and video, right? Essentially, you can turn on your camera and then point it at your face and ask the model, what do you see? And the model will tell you, describe you, or describe what it sees on the camera, right? And so that's live multimodality. That's essentially bidirectional. You're sending things back and forth, which means the connections will be long and they will be sticky, right? So a typical round robin load balancer wouldn't know how to handle this. And last but not least, sometimes what you might want to do is you might prioritize certain traffic over certain other traffic. Let's say you have a single load balancer that is exposing multiple models behind the scene. You might want to configure a policy to say if my chatbot traffic increases, because a lot of users are on my website talking to the chatbot, I want to prioritize that traffic over my data analyst doing summarization or doing batch processing or something like that, right? So you might want to also do that. So for these particular reasons, so these are some examples. A code assistant have a very large context window. So a code assistant particularly will benefit from caching because the code or the prompts you're sending back and forth is more or less the same thing. It's just the same code base, and the developer is just iterating over the same code base with new prompts. So if you send the code base the first time, you can just tokenize it and cache it. Next time the next prompt comes, you skip the entire tokenization phase because you already have the code tokenized and stored. A chatbot also could benefit from caching, because a chatbot, essentially, as I said, is like a bunch of questions and answers. And each time there is a new question, you're just sending back the previous questions and answers. So if you cache those, then you don't have to process them again. A generative AI large language model may be very low on cache utilization, because the user might be either sending new pictures each time to edit, or to detect objects in that picture, or just the picture itself is changing between each time the user is talking to the model. So the model will not benefit from using caching. And a lot of times, some of the prompts are actually so small that it's not even worth doing prefilling for them, right? I talked about these two phases, the prefill and decode phase. Sometimes the models, the prompts are so small that there is no point of doing prefilling, because you're not gonna benefit from caching them. You can just run directly into the decoding phase. So we covered some primitives or some primer around generative AI, inference specifically. We covered how running models on Kubernetes works, and how model or large language model traffic is not the same as web application traffic. Now I have one more piece of the puzzle to cover before we get into LLMD, and that's the Gateway API, and specifically the Inference Extension. Do you want to do questions during the session? I'm happy to do that, if you have any questions. Yes?
I have questions about if, for example, the model is deployed in Kubernetes service with different multiple hosts, and each Kubernetes node has a different cache, as you say, around 25%. Then how the traffic network traffic could be routed, because every node has a different cache, and if you are on the continuous conversation with a model,
Yes.
so it might be difficult to route the traffic.
Yes.
So
the question is, if you are running on top of Kubernetes with multiple backends, multiple pods, and if each pod has a different cache, or each node has a different cache, how do you handle that? I'm going to talk about it later in the session, but roughly the two methods are the following. Some of the accelerator models, specifically for NVIDIA, support inter-GPU high traffic bandwidth for cache transfer. So you can actually transfer cache from one to another, right? This is one of them. The second one is to do session affinity. If you want the same traffic from the same user, let's say a chatbot example, to go the same pod, because as I explained in the example, I said that chatbot will benefit from caching because you're basically sending the same questions over and over again. You can just add a header in your request and then configure the backend to, based on the header, to forward to the same pod on the backend. So you can create like sticky sessions by having traffic going to the same pod, so they can utilize the caching on that particular pod. Make sense? Any other questions about everything I talked about now? Either everybody understood everything, or no one has an idea about what I'm talking about. We can't use HTTP? HPA. So you can. It's just that you're not going to be able to use the standard metrics in HPA, because horizontal pod autoscaler supports CPU and memory as a metric, right? So if you want to do autoscaling with HPA, you will have to use custom metrics, right? So depending which cloud provider you're running on, or if you're running on-prem, I think HPA, the open source library, support custom metrics autoscaling. So what you will have to do is set up Prometheus to scrap metrics, and then configure HPA to look at those custom metrics and autoscale based on those, not based on CPU and memory. Make sense? Yes. Right? If there are no other questions, I'm going to skip straight into Gateway API. So now, I want you to all bear with me. I'm going to do a recap at the end. Put everything I just talked about aside, and let's talk about the Gateway API. How many people here know what the Gateway API is? Few people. How many people here know what the Ingress API is? All right. How many people had sleepless nights because Ingress was broken? OK, few of you. Good. All right. So the Gateway API is a new API that was introduced to Kubernetes back in 2019. And it's meant to replace the Ingress API. As of now, the open source project, Kubernetes, they're not introducing any features to the Ingress API. If you go to the Ingress API GitHub repository, it will say that Ingress is on maintenance mode. So they're only fixing bugs, but they're not introducing any new features. Most of the development being done open source in the open source space is focused on the Gateway API. Okay? What does the Gateway API does different than Ingress? Well, Gateway API introduced a bunch of new object types that allows you to do a multi-persona type scenario. typically, if you are using the gateway API, so if you are using the ingress API, what you do is you create a Kubernetes service, you create ingress, and you point the ingress to the Kubernetes service, right? Very simple. Couple of things to keep in mind. Ingress only supports backends that are in the same namespace. It cannot point to backends in a different namespace. So if you want an ingress to generate a load balancer that points to an app, that app has to be in the same namespace as the ingress object itself. The gateway API was introduced to solve two problems. Cross namespace reference, because the gateway API does support cross namespace reference, and multi-persona. So in a gateway API space, you will have the gateway classes, which are defined by your platform. So that's basically, gateway class is a definition of the type of load balancer supported by the cloud platform that you're running on. So that could be things like internal load balancers, external load balancers, HTTP load balancers, TCP load balancers, UDP load balancers, extra. Then a gateway is what defines the actual load balancers. When you create the gateway, a load balancer gets provisioned. Then in each of the namespaces where the users are defined in their applications, they can define a service, a Kubernetes service with capital S as typical, and then they use an HTTP route to map a gateway to their service. So in other ways, it could be that in the platform admin defines all the gateways, all the load balancers in a central namespace called infra namespace, and then the different developers, the different users consume that gateway through the HTTP routes, right? So in a gateway world, you will have to basically create three objects. A gateway object, an HTTP route object, and a service object. So there is one more object compared to ingress. Now, you might notice that it says HTTP routes. Does that mean that there is other types of routes? Yes. As of now, HTTP routes is the only one that is GA, but there is also TCP route, UDP route, gRPC routes, and I believe that's it. Yeah, there is a TCP route and UDP route. Now, some of you might say, well, Kubernetes itself does support deploying TCP load balancers using a service of type load balancer, right? When you create a Kubernetes service, the type of the service of that particular service can be load balancer, and that will generate a layer 4 load balancer. That's why they have prioritized creating HTTP routes, because the gateway API is designed to do layer 7, but it will be able to do layer 4 coming very soon. This is how it will look like typically. You have your cluster operator defining a bunch of gateways. Those are the load balancers, and they can define the TLS certificates, they can define the policies, they can define a lot of things. Then a store developer will be able to consume that gateway through an HTTP route. In the HTTP route, they can define the paths /store/star, and then which services they point to. They can also define here traffic splitting. So they can say, I want /store/star to send 20% of traffic to V2 of my foo store, and then 80% to V1, canary deployments, or 50-50. Or 100-100, whatever you want to do, right? This is just another example of a weighted load balancer, 90-10, etc. The reason I'm showing you all these examples is because when we will get to LLMD, these examples will be relevant because LLMD leverages those concepts. So you can imagine, for example, that this login service 1 and login service 2 that you see here, those could be large language models. Large language model variation 1, large language model variation 2, and then you can just do a canary deployment by saying 90% of traffic goes to version 1, or version 1, 10% goes to version 2, right? Then, about 2 years ago, a new extension was introduced to the Gateway API called the Inference Extension. So the Gateway API Inference Extension. So what does the Inference Extension do? It introduces two new objects, one called an inference pool and one called an inference objective. So an inference pool is essentially a collection of model servers. So you will run your models as backend pods, and then you will group them using an inference pool, using labels. You create an inference pool, and you say, this inference pool is my Gemma 1, Gemma 3, Llama 3, Mistral, whatever, right? And then you use the HTTP route to point to the inference pool. So this allows you to do a bunch of things, including using the same gateway API to handle large language model traffic and regular application traffic, right? And then one more component that this inference extension introduced is something called the Endpoint Picker, EPP, or the Endpoint Extension, EPE. Well, normally we call it EPP, the Endpoint Picker. What is the Endpoint Picker? The Endpoint Picker is a pod running inside your cluster that download metrics from the model servers, from the large language model, and uses those as a way to route traffic intelligently. So your request comes from the user. You notice here this is the same structure as the OpenAI I showed earlier, right? /v1/chat/completions. The request goes to the gateway. The gateway forwards that request to the endpoint picker. The endpoint picker can be configured to pull metrics from the model servers. So this would be the example of custom metrics. Tell me what's the KV cache utilization. Tell me what my depth, the queue depth look like. So how many requests are being queued to be processed by a particular backend pod, et cetera, et cetera. And then uses those metrics plus any policies that you define to tell the gateway where to route the traffic. So what can it do? It can do something called model-aware routing. You remember earlier when I showed the example here, and I said that one of the particularities of OpenAI is that you have to specify the model inside the request, right? The Gateway API by default cannot read inside the body of request. The Gateway API can only look at the request path. But the endpoint picker can be configured with something called body-based routing, BBR, to dig into the request and then grab the model ID. Why would this be useful? You might actually have a single load balancer pointing to a Llama model, a Gemma model, and a Mistral model, right? And then the user will use the same IP address, the same load balancer to send traffic, and then just based on the model they're trying to talk to, you can route it to the right backend, right? The second one is serving priority. So you can actually, in the HTTP route, define priority the same way you define weight load balancing. So, 90% of traffic, 10% of traffic. You can say, I have traffic coming for my chatbot. I have traffic coming from my summarization. I have traffic coming from my internal test developers, right? I want to prioritize chatbot traffic. So you can just set up a policy in the endpoint picker to say, if traffic is coming from a chatbot, just prioritize that first. Drop all the other stuff. And then it has also a built-in mechanism for either a fail close or fail open fallback. So by default, the endpoint picker functions in a fail close manner, which means if there is no enough capacity to serve the request, it will just drop it. It also has the possibility of model rollouts, which I just talked about, essentially rolling a new version of the model and then splitting traffic across the old version and the new version. So this is all possible via the Inference Extension. The Inference Extension does not change fundamentally how the Gateway API works. It just adds an extra component called the Endpoint Picker. And the Endpoint Picker can be configured, as I said, to look at metrics, download metrics, and use them to do intelligent routing. So let me show you an example here. It's not a fully blown example, but it will give you an idea about how it works. So I have downloaded, installed, what have I installed? I have installed a Gemma 3 model. So this is a Gemma 3 deployment, very similar to the one we saw earlier, running VLLM. I'm running a different version of VLLM, but it's not very important. But the same thing, just a number of GPUs, a bunch of parameters to the model, blah, blah, blah. The only difference here, I added some readiness probes and some liveness probes in this particular example. I'm going to give you the GitHub repository if you want to look at it. But these are actually very useful if you're running large language models. You remember earlier that I talked about the fact that when you run the model, if you run VLLM with the option to download the model from Hugging Face, there will be a time when the model or the pod itself will be ready, or the container will be ready, but then it's not ready to serve traffic yet because the model is not fully loaded. Well, adding a liveness probe and a readiness probe will be useful. So VLLM exposes a /health, and if you query /health when the model is being loaded, it will return it will not return 200. So you set a liveness probe to say, up until the point that my /health returns 200, don't set the pod as ready, and that will have a trickling effect inside of Kubernetes, because as long as the pod is not flagged as ready, the service will not be modified to point to the pod, the load balancer will not be modified to point to the pod, right? So just keep that in mind. I have a startup probe, blah, 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 a bunch of things. So I'm going to show you this now in a second. I want to show you something else. I also downloaded, I deployed a gateway. So this is how my gateway looks like. It uses this gateway class. This is normally how you tell the gateway which type of load balancer you deploy, by pointing it to a specific gateway class. These are very specific gateway classes inside of GKE, but the gateway classes could be dependent on your particular load balancer or particular cloud provider that you're running on. If you're curious about how do we... So I talked earlier about the fact that in the gateway API, the way you would map a gateway load balancer to a particular service backend is using the HTTP route, right? So the question is there a way for me to limit which HTTP route can be mapped to which gateway? Yes, there is. Allowed routes. This is one where we say we only allow routes that are coming from the same namespace. But you can also be selective, and you can say only allow routes coming from this list of namespaces. Then I have my inference model running here. So this is another object. So this will create the inference pool. So the inference model is just an object that defines, OK, I have one model running. It's called Gemma. And this is the model name. And this is where I set my criticality. So if you want to do priority-based load balancing, you set it in the inference model. You say, this is standard, which means it's not very critical, but you can have multiple levels. I think it's critical, standard, and critical, if I'm not mistaken. These are the three supported values. And that's basically how you would do priority-based routing. So in this particular case, the endpoint picker will read this criticality level, and it will decide, OK, this inference server is, these are the critical ones, these are not the critical ones. This is also how the endpoint picker knows where to route the traffic, is using the model name. So this is the model name here. Will be read by the endpoint picker, and then it will also read the model ID coming from the body of the request, and then it will map the traffic to the right pod. Then I have my HTTP route here, which just uses the inference gateway I talked about earlier, defines a path, which is /v1, and then if the path matches /v1, forward it to my Gemma 3.1b pool. And this is, in the HTTP route, is where you define what we call the weights. So the weights is basically the percentage of traffic you want to send to a particular backend. So this is an example where you might do something like that, for example, and then do this. And let's say that you are introducing a new v2 of the same model, so model rollout. You create a new inference pool called v2, and then you do something like 0.1. And then here you do 0.9. This would be how you would do weighted traffic splitting across multiple versions of the model. Then I have my, that's it. I have my HTTP route, that's it. So I have it here. I can look at it real quick. I'm not going to save this. I'm just going to close all of that. And let me show you in a second. I'm just going to scale back the deploy bit. I don't know if it's ever actually scaled up, but it's fine. We showed all of that. So this is using the gateway API, which means the IP address is public. You can actually talk to this if you want. And I'm just going to send the same exact request. And I'm going to time it because why not? So this request will take a few seconds to run. It's the same model, and I'm using the same exact parameters, right? The same prompts, the same everything. One thing you will notice right away is that this is already taking way less time than the previous model, because the previous deployments, I'm only using the standard load balancer. Here, I am using the gateway API with the Inference Extension, which is LLM aware. So it's able to optimize the traffic better. If I do a kubectl get pods, you will notice that I have two pods. I have my deployment, and then I have my EPP, the endpoint picker, right? So the endpoint picker is the component I talked about earlier, which basically the gateway will talk to, and then it will tell it where to route traffic to. So if I scale up my deployment to 10 instances, then the EPP will be aware of all these instances. Yeah, one more thing actually I didn't show earlier is, let me try to see. I think it's this. Yeah, regardless of which models you're running on, the gateway API in combination with VLLM has actually a very particular endpoint called v1/models, and that's part of what the gateway API called model discovery. Because when new models are spun up, they will be registered with the Gateway API, with the Inference Extension particularly, and it will be aware of them. And so if you query these V1 models, it will tell you actually which models are running in the backend. So in this particular case, I just have one. If I run this through GQ, so I can get a better visibility, it tells me I have one model called Google Geometry, and it actually might even, sometimes it might, I don't have it here, but sometimes it might even have some extra information about the model utilization. It will know how, it will tell you how much KV cache is used, how much the queue depth is, and stuff like that. So yeah, this is basically the Gateway API Inference Extension. It just extending the Gateway API to be more model aware. So I'm going to quickly recap what we talked about so far. We talked about prefill and decode, right? The two phases of large language models. One is compute bound, one is memory bound. I think just based on this particular slide and everything I talked about earlier, if you've been following, you might understand that the point we're going to get into is splitting these two things into two different specialized backends instead of trying to do them on a specific, on single same backend. We talked about how LLM requests or how the traffic profile is not the same as web applications, that you need some sort of load balancer which is LLM aware that knows which load balancers are running, which models are running and how busy they are. The inference extension gets us to the point where we know which models are running in the backend, and we can do some sort of intelligent routing with either weights or priority or something like that, but it doesn't get us all the way there. And then we talked about the Gateway API and the Inference Extension with the Endpoint Picker that I talked about and the body-based routing. So body-based routing, we read the model name from the OpenAI spec and routes the traffic to the right model, and then the Endpoint Picker can use metrics to make smart routing decisions. Now we get to LLMD. Where does LLMD fit in all of this? And you will understand now why I had to do this long introduction, because if I would have jumped directly into LLMD without the right context, it would be quite hard or quite confusing to understand. So LLMD is not a project in the sense that it's code. LLMD is a project that is trying to define patterns for distributed inference on Kubernetes. It leverages all the stuff I've been talking about so far. It leverages Kubernetes, it leverages the Gateway API, and it leverages the extension. And then it adds few of its own things. So LLMD has a custom version of VLLM, so it doesn't use the standard vanilla VLLM. They repackaged VLLM with a bunch of extra metrics. And then it has a custom endpoint picker for the inference extension that I talked about. The way LLMD likes to say this is LLMD defines well-lit paths. What are these well-lit paths? One of them is something called intelligent inference scheduling. So this basically deploys VLLM behind the inference extension gateway and uses caching to decrease the latency. And that's the demo 2 I showed. You saw the demo 2. I deployed the same exact model using the inference extension and the Gateway API, and I was able to drop basically my request processing time from 10 seconds to 5 seconds, right? So that's the first thing. What particularly this intelligent inference scheduling does is that the custom version of VLLM that LLMD runs exports a bunch of metrics, and some of these metrics are the GPU memory utilization, the KV cache utilization, the queue depth, and a bunch of extra metrics, and uses those to distribute traffic evenly across all the pods running in the backend, right? And then it adds an extra well-lit path called Disaggregated Serving, or Disaggregated Prefill Decode. Disaggregated Prefill Decode essentially runs prefill and decode on dedicated instances. Instead of running on the same instance, it runs some pods for decode, some pods for prefill. It's all configurable, it's all customizable. I'm going to show you some examples. This is how the architecture of LLMD looks like, and this answers part of the question that was asked earlier, which is the prefix caching shareability across multiple nodes. So in the backend, starting here, I have a bunch of VLLMs. What I'm doing, this is disaggregated serving. I run some of these VLLMs in a prefill profile and some of them in a decode profile. to share the cache across the instances, you can either use NIXL or DCN. These are NVIDIA technology that allows you to transfer memory between GPUs, right? Or you can actually use an external independent caching layer. It supports LM cache, it supports Dynamo, which is part of NVIDIA, and it supports using the host memory as a cache layer. And there is actually work on supporting the database as a cache layer coming soon. So this will work on the same, I think LM cache can do multi-instances if I'm not mistaken. I'm not sure about Dynamo. Now, obviously, one of the things to keep in mind is that if we imagine this gray box as a single instance, and I have multiple instances, how good the caching works will also depend on the network traffic between the instances. So I have to have some sort of high bandwidth network traffic between instances so I can either transfer cache or share the cache across instances, right? It uses the inference gateway, which is the gateway API that I talked about. It's Envoy-based, by the way, for those who are curious. It has a body-boused routing, which is configured by default. So this is the thing that will look at the model ID in the request and route the model route request properly. And then it has an inference scheduler. This inference scheduler is EPP. It's the endpoint picker. It's just another version of the endpoint picker, which does scheduling in a different manner. It picks the endpoint using multiple metrics as an input. One of them is how busy the backends are, and a bunch of other metrics. I'm going to show you some examples in a bit. So disaggregated inference is essentially splitting prefill and decode into dedicated instances. Sometimes you might want to even split them into different types of accelerators, because some accelerators are good for prefill, some accelerators are better for decode. So you split them across multiple instances. This is the version of EPP, endpoint picker, that LLMD introduces. This is what it does. Inside that scheduler, they call it scheduler. I find the word a little bit scheduler, this component here, this inference scheduler, I find it a little bit confusing because it does scheduling in the sense that it does scheduling for the requests. It schedules requests to backend pods, right? It doesn't place pods on nodes. It just schedules the requests and route them properly. It runs a sort of a pipeline inside, and that pipeline has 3 steps: a filter, a scorer, and a selector. So a filter is the first step for each request. So I can imagine requests are coming here. The filter, what it does basically, it will filter out the pods that are not going to be able to serve the traffic. So imagine those are the model servers. Those are like the actual pods running the actual large language model. The filter will basically say, OK, I have 10 pods, but these 3 are too busy. They have very large queue, so we're not going to consider them. Then it assigns a score to each backend, and then it selects a backend to send the request to. I have a bunch of examples here that I'm going to show you. I found those in a YouTube channel. So they are screenshots of a YouTube video. So I'm sorry if the quality is a little bit too low, but I'm going to run you through some examples because I like them. So this is an example where I have a very short prompt. Hello, how are you? So in my particular case, I have 2 pods that are set to be prefill, 2 pods that are set to be decode, and then 1 pod that is set to be both, right? So the request comes in. That intelligent scheduler we talked about will kick on, and it will assign a score to each of the pod. Because my request is quite short, there is no point of doing prefill in this particular case. So what it will do, it will just score higher the decode nodes because it realized that the prompt is short. By the way, this is a configurable parameter in LLMD. You can configure LLMD on a threshold. So you can tell it what's the maximum number of tokens that will trigger a prefill and a decode. Otherwise, if it's below that value, it will just go straight into decode. And then in this particular case, it selected VLLM decode 2 simply because it has a queue of 0. You remember I was talking about the queue depth? That's essentially how many prompts are waiting to be processed by that particular instance. Well, it looked at this one has a queue of 1, this one has a queue of 0. So it gave this one a higher score compared to this one. And then this, so that's the scorer part of that pipeline I talked about. The scorer part here, and then the select will be to select VLLM decode 2. If we look at a different example where I have a much larger prompt, so the prompt is has 150 tokens. In this particular case, it selected the Prefill instance number 1, and then Decode instance number 2. It gave them a much higher score. Because, let's see why. Because Prefill instance, well, first of all, it already decided that it needs to do Prefill and the Decode because the prompt is very big. Prefill instance number 2 has a queue of 2, but it has a very high cache value. There is a lot of tokens cached on this particular instance. So it selected this one. This one has a very low cache value, right? So it's assigned a higher score. And then VLLM Decode number 2 is because it has a lower queue size. So it scored these 2, so the prompt will go to Prefill number 1, a cache transfer to VLLM Decode number 2, and then the prompt will be generated and the results will be sent back to the user. This is an example where we have a much higher, this is an example where I have very high load. You see each of the instances has a pretty busy queue. So this has queue of 10, queue of 5, queue of 15, queue of 20. So it will select these 2 because they have the smallest queue. This is the filter part of that pipeline that I talked about. So the filter will decide, okay, the pods with the higher queue size will be filtered out, so I'm not going to even consider them, and I will just select these 2 and then give them a score and then send the request there. So the request will go to VLLM Prefill 2, then it goes to Decode 2, and then the prompt will be generated. And the large one is an example of sticky session that you asked about earlier. So this is where we assign a header to the request. So we can say this is, so you can see the prompt continues our previous conversation with machine learning algorithms, blah, blah, blah. This is where you want to specifically assign a sticky session to a particular pod because you know that that pod has already the tokens cached, right? So LLMD supports all of this. You can do sticky sessions with headers, or you can configure a threshold for how many tokens to skip the prefill for, and then by default it will download or it will look at the metrics like the queue size, the KV cache utilization, the memory size, etc., etc. Right? So that's the intelligent scheduling part. So I have here, for example, this is a benchmark using Llama 2 70B. And in the left side, we're running a prefill on an L4 node. On the right side, we're running prefill on the left side, we're running prefill and decode on L4. On the right side, we're running prefill and decode on A100. And you can see already that there is a huge difference between the performance of the so what we're looking at, the tokens per second, obviously, that's the metric that we're looking at. And we're looking here that the performance for the prefill is better on L4, but the performance for the other way. The performance for decode is better on L4, and the performance for prefill is better on A100, right? So this is an example where disaggregated serving or inference makes sense by splitting the prefill and decode into 2 different instances using even completely different accelerator types, right? So I have a quick demo here that I will show you. And let's switch back to this cluster here. Give me a second. So I have this cluster here. I have this particular namespace here, and I have this endpoint here. Similar to what I showed you earlier, but if I do get pods-n $namespace, I have 2 pods running. I have 2 decode pods running. Those are both running, I think it's Llama, if I'm not mistaken. We can look inside this kubectl describe pod, and let's describe this particular pod. And this is running which model? What is the model name? Well, actually, I don't even need to know from here. I can just query the load balancer on the, it's running Quen. Sorry, I forgot. Yeah, it's running Quen 0.6b. So both my instances here are running the Quen model. I know, not this one. So this particular deployment is using LLMD. So I have 2 model services running, both of them running the same exact model. You will see already that inside there is actually 2 containers inside each pod. The 2 containers are an init container and VLLM. So VLLM is the serving engine, and there is an init container that sets up the pod so that it can send the metrics. And then I have my EPP here, my endpoint picker. right? Which is deployed as part of the Inference Extension. And so if I query it now with a curl command, it will be relatively quick. It's quite fast. That's because, although in this particular case, I am not even, so it took like only 4 seconds to get the response back. In this particular case, I only have Decode nodes. I don't have Prefill nodes because I just didn't want to deploy it. But the request processing is very fast just because I'm running with a model or with a setup where it's optimized for caching, it's optimized for all these things that we've been talking about. So my processing will be very fast. There is actually a way for you to, I think it's, I forgot what it is. I have to go dig it up, sorry. No, I know it is, sorry. So if you are trying this later, you will be using the LLMD. This is the GitHub repo. Inside there is guides. And inside guides, there is this prefill decode disaggregated. And inside that, there is a threshold value here. I think it's either here or here. I think it's here. You can see, yeah. So this particular example, this PD disaggregation, this will deploy LLMD with disaggregated profile, like prefill and decode instances. And here you have a parameter threshold value. It's by default set to 0. So if you deploy it as is without changing this, it will only deploy the decode pods. But if you set it to a value, that's the threshold for the number of tokens over which to skip the prefill phase. So you can set up to 100. So small prompts doesn't do prefill, and then big prompts will go through the prefill and decode phases. And then it has like a bunch of parameters that you can change. So I'm going to stop here because we are almost halfway through the session, and I don't think I have more contents. I think we're going to probably end a little bit early. But I want to stop here to see if there are any questions or anything in particular that you want to discuss before we move on. Or I start asking questions to see if you've been following. All right, no questions. Good. So we ran a bunch of benchmarks, and there is actually an open source benchmarking framework for LLMD. It's available on GitHub. I'm going to share the slides with you later. You can use that to basically run LLMD in one of these profiles, either in the disaggregated profile for prefill and decode, or without the disaggregated profile for prefill and decode, and then run a benchmark to try to figure out which profile works better for you, depending on which large language model you're running in the backend. And this is the moment where we go a little bit beyond routing, because everything I've been talking about so far covers pretty much, I'm going to stand a bit. Everything I've been talking about so far covers pretty much only the network traffic part, right? We've been talking quite a lot about the network traffic. How do you get prompts in, and how do you configure them, or how do you configure a language model to handle traffic which is uneven, et cetera, et cetera. Now, I want to go a little bit beyond the routing side of large language models. What we've seen so far is just doing single host serving. So running all your language models on a single host with a single GPU. All the models I've seen so far or showed so far run on a single L4 GPU. You might have a situation where you do multi-host serving, or sorry, multi-accelerator serving. So running the same model across multiple accelerators. In this particular case, you will basically use whatever GPU KV caching transfer technology to be able to move cache from one GPU to another. Specifically when you do prefill decode as disaggregated, right? But then there is another situation you might run into, which is the multi-host, multi-accelerator. I talked about it earlier, the example of DeepSeek I showed earlier, the big full quantization model, which requires 1,370, was it, of like memory split across 52 A4 or something. And I talked about the fact that you cannot fit more than a certain number of GPUs per node, which means you will need to split the model itself across multiple physical nodes, right? For that, Kubernetes has an API called leader worker set. It's an API in Kubernetes, open source, that allows you to basically split pods across multiple nodes, but handle them as a single unit. So in leader worker set, you will have pods running as stateful sets in the backend, and then you will have a leader. So you see, if you look it up later, in the spec of LWS, you will have a leader section and a worker section. The leader section defines which of the pods is the leader, and then the worker section defines how many replicas or how many instances you want to run your stateful sets on, or you want to run your pods on. And the way it works is that that particular leader that you have defined becomes the endpoint that traffic goes to, because that leader is aware of where all the other pods are, and is also aware of how the neural network is split across multiple nodes. So all traffic goes to a single pod, and then that pod will run on top of, or will split traffic or send it to the backend pods. So it kind of acts like a load balancer. As of now, LLMD doesn't support AWS, but it's on the roadmap. It's coming. I will leave this QR code here if you want to scan and go into. This is like an article that we have published about leader worker set on Google Cloud. Good? All right. So back to this slide. We talked about a lot of things. So to recap, large language model running large language models in production means that you have multiple layers that you might want to optimize. Everything I covered so far only talks about the network side, but there is other things that you might need to optimize. And we talked also about how the fact that your typical vertical optimization or vertical autoscaling and horizontal autoscaling, the standard ones that you would use for web applications, doesn't work for large language models, and you need to think about it differently. So one of these optimizations is storage optimization. I showed the example of Gemma 3 running on top of VLLM, and showed you how it takes about 2 minutes to download VLLM itself and another 2 minutes to download the model, right? One potential solution to that is to pre-bake the model inside the container image. Start with the VLLM, vanilla VLLM container image, download the model, put it inside that, and then you end up with a very fat container that has the actual model and the weights and the serving engine, right? But then you will end up with a different problem, which is a very big file. How do you optimize for that? There are 2 ways you could do that. So this is the problem I talked about for autoscaling. You'd autoscale a VM. It takes some time. It takes some time to pull the container image. It takes some time to download the model. It takes some time to load the model into memory, etc., etc. So how do we optimize this? One way is to do something called container image preloading with attached disk. Kubernetes has something called Kubernetes Image Pooler, which essentially allows you to preload the container images into the nodes, even if you don't need them. It's a bit wasteful on the storage side, but storage is relatively cheap compared to the time you would waste to download the model each time, or to download the container each time you need it. So what image preloading means, essentially, is that you run a component on each node in the Kubernetes cluster. So whenever the Kubernetes cluster triggers a scale-up, a node spins up, and the componented node will download the models and then have them available in the node. So in case of a trigger of a scale-up on the application itself, and then a pod ends up being scheduled on the node already has the container image. So you skip the few seconds it will take to pull the container image. Make sense? So this could be useful if you are doing the thing I talked about, which is pre-baking the model inside the container image, right? There is also another project, which I didn't show here. It's called Spiegel. It's pronounced a bit weird, this Swedish word. It's called Spiegel. I think I have it at the end of my slides or in the show notes. And it's basically a distributed image caching on Kubernetes. If you don't know this, Kubernetes open source uses Containerd as a runtime, as a container runtime for containers. It doesn't use Docker by default. And what Spiegel does is that it sets up Containerd in a mirroring configuration. So what happens is when a node needs to pull the container image, instead of directly pulling it from the artifact registry, Spiegel will find it in the cached on another node and then download it. And that should be faster because you're downloading from the same node using hopefully fast network traffic instead of downloading from the internet or from a remote endpoint. And then the other method you could do is using file system mount using Fuse. So if you are using something like S3, if you're on the cloud using something like S3 or Blob Store or Google Cloud Storage, you could actually mount a bucket as a volume inside a node. So you could create a bucket, put the model inside the bucket, and then mount the volume inside the node in a very specific path where the container or the serving engine expects the model to be. So essentially, you spin up VLLM, and then you figure out where does VLLM drops the model weights when it downloads them, and then you just create the same exact volume in the same exact path with your model and your weights preloaded there. So when VLLM starts, it just checks the folder and goes, okay, the model is available, I'm just going to load it. And that should allow you to cut some time on the time it takes for pulling the container image and then pulling the model itself. You don't have to use one of those strategies. You can use both. You can use preloaded containers plus volume mounts using Fuse driver. Another method is to use something called LoRA adapters. So LoRA stands for low something ranking adaptation. I forgot what I think it's low ranking adaptation. I think the O is part of low. So LoRA, what it is, it's essentially an adaptation layer for personalizing the last couple of layers of the neural network. Let's take an example. You have a prediction service which runs a large language model. And the prediction service talks or is optimized to talk English, but you want to be able to serve English, Japanese, and French. One option you could do is take that large language model and retrain it in 3 languages and run 3 times the same exact model with 3 different languages. Another way is to do an adaptation layer. The adaptation layer is a thin model which is trained only to do translation. So you would invoke the actual large language model, generate the tokens, and run them through the LoRA layer so that it does the translation for you. It's very good for like translation. It's good for, it's mostly good for translation actually, for adapting the language to speak multiple languages, or adapting the model to speak multiple languages. So this hopefully should allow you, because those like LoRA layers, they are very thin and very light, they don't require any accelerators. So they can run without GPU. So that allows you to either, instead of running 3 different models that requires a lot of accelerators, you just run a single model, and then you adapt the output based on what you're trying to achieve. This is how it looks like on Kubernetes. You would spin up the model. This is VLLM. So you have the model ID, and then you have LoRA adapters passed as a set of values. And then when the user makes the request, in the body of the request, you specify the model ID and then the LoRA adapters you want to use. I'm going to quickly talk about this open source project. I think that these are my last couple of slides. I didn't need the entire 3 hours, but Kueue is an open source project which is designed for doing job batching on Kubernetes. So if you don't know this, Kubernetes does support jobs, right? So your job is just basically a piece of container that has a known start time and a known end time. So it runs and then stops running. It does also have a cron job API, which allows you to run things in a cron manner. But what it doesn't do is it doesn't have intelligent way to figure out which jobs to run before which, like prioritization, for example. It doesn't have a very good way to do resource sharing across multiple jobs. So let's say, for example, you're a platform engineer or a platform admin, and you have a Kubernetes cluster with a finite amount of resources. Let's say 10 GPUs, right? And then you have a bunch of teams that are running jobs to train their models on your cluster. And then you go to them in your Slack channel and you say, hey, please, guys, be nice. Can you please set the priority to the right number depending on how critical is your workload is? How many do you think will set their priority right? Everybody will set their priority to the highest absolute value because everybody thinks that their job is the most important, right? So how do you enforce this? Kueue. So Kueue allows you to basically create an abstraction layer on top of the job API, and then allows you to define policies. So you can say things like, these jobs can only run during the night when my cluster is at the lowest utilization possible because they're not very important. Or if I have this amount of resources available in my job, in my cluster, I want you to splice them evenly across multiple teams, right? Using budgets. So you can say 10 GPUs, each team gets 1 GPU. If one team is not running, then you can relocate the GPU somewhere else. But then if they are running again, you can just relocate it back, right? This is how it looks like. It's basically a bunch of YAML files. And you can define a quota based on the namespace itself or based on the cluster. So the quota could be things like CPU, memory, GPU, etc., etc. And then it will basically just monitor the quota, look at your policies, and then run or preempt the jobs depending on what you're trying to achieve. And then the last thing I'm going to talk about, I covered this very briefly, but this is actually one of the most exciting things coming to Kubernetes, I think. It's called DRA, Dynamic Resource Allocation. It's a project that is meant to optimize resource allocation in Kubernetes. So if you let's take an example. If you have worked with storage in Kubernetes, you know that the way storage works in Kubernetes is that you have something called the storage class, right? Storage class defines the type of storage the cluster has. Fast SSD, slow HDD, blah, 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 right? And then you, as a user, you create a claim. And the claim is essentially against the class. You say, I want a persistent volume claim. My persistent volume claim should have 100 gigabits against this particular type of storage. DRA functions the same way. You can define a set of resources available in the cluster, GPUs, TPUs, blah, blah. It's actually created in such a way that it becomes generic, and I'm going to give you a very particular example why this would be useful for. And then a user, or a workload can claim some resources using the API for DRA. So the idea here is to make claiming resources in Kubernetes easier, more dynamic. Instead of the way we're doing it right now, which is the examples I showed earlier, you have to have a node selector to say, schedule this pod on this particular node, and then using the resource request to say how much resources do you need. One very particular example, which is completely, this is unrelated to large language models in GenAI. Imagine you have a workload that needs to egress with a static IP, right? Say, for example, you are running a banking application, and you call a remote gateway API, a remote payments gateway. That remote payment gateway will allow list you based on the IP address. So the provider tells you, give me which IP address you're going to be calling me from, and I will only allow list that particular IP address. Today in Kubernetes, that's not possible. Because the way Kubernetes work is that if your workload on a node is talking outside of the cluster, it will either appear as the pod IP or the node IP, right? So most probably the node IP. Because the pod IP will be natted behind the pod IP, the node IP, and the node IP will be the one visible outside. The problem here is you cannot predict which node your workload is going to end up on. So if your workload changes node, it will have a different IP. With DRA, what you could do is you could run a bunch of pods, and then you can use DRA to say, give me a single IP address for all traffic outside of the cluster. So you have a static IP address for all the traffic talking outside of the cluster. And with that, that's all I had today. Sorry I didn't need the 3 hours. Maybe that was a good thing because you don't want to hear this voice for an extra hour 15. I hope it was useful. That's my link tree. That has a link to my LinkedIn. And I'm going to make the slides and the code available in GitHub. And I hope this was useful. We have... They already cut the sound? OK. They just want me out. Do you have any questions? I have one more QR code for you. Feedback, please. This will take you to my page on the DevOps schedule, and you can leave me any feedback. There was a question in the back? No? Was it useful?
Yes.
Was it a waste of time?
No.
OK, good. Please give me feedback. I'm really hopeful that I will get some actionable feedback because this is the first time I present this content, and I want to know what kind of things I should talk more on or talk less on, or what things I should probably focus more on or less on. Or if this was terrible, just tell me this was terrible, don't do it again, and I will stop. I will probably not, but thank you so much.